Hey there, and welcome to This Explainer. Today, we're tackling one of the most profound, literally mind-bending mysteries of the entire universe. What exactly is mass? I mean, we interact with it every single day, right? We feel its weight, we push against its resistance. But when you zoom all the way down into the quantum realm, that solid, dependable nature of mass completely dissolves. It turns into this wild symphony of waves, phases, and spinning energy. Today, we're going to structure our time a bit like a presentation of a cutting-edge physics paper. We'll trace the evolution of mass, mapping the journey from Einstein's theory of relativity straight through to the incredible geometric unifications of our space theory.
Here is the roadmap for our presentation. We'll be hitting 6 key milestones. First, Einstein's equivalence. Then, Schrödinger's equation, followed by Feynman's path integral, our space projection, vortices in action, and finally, our big conclusion, answering the ultimate question, what is mass?
All right, let's dive right into Section 1, Einstein's mass-energy equivalence.
Now, back in 1905, a little equation called E equals mc squared completely revolutionized our understanding of reality. It boldly stated that mass and energy are entirely equivalent. But to really appreciate this massive paradigm shift, we have to remember how we classically define mass. Classically, we just think of mass as the physical stuff inside an object. Or, if you're thinking in Newtonian terms, it's an object's inertial resistance to being pushed or accelerated. But Einstein, he challenged this static, boring view with a truly brilliant thought experiment involving light.
Imagine a box, and it's emitting 2 photons in perfectly opposite directions. To someone just standing there watching, the box doesn't move. But if we view this exact same setup from the perspective of an observer who is moving past the box, special relativity kicks in and tells us that time actually slows down. Because of this time delay, our moving observer sees the light's frequency, and therefore its energy, as being higher. But wait, here's the catch. The total energy of the system has to be conserved. It's a fundamental rule. So if the light's energy appears to increase, something else has to decrease to balance the books. Since the relative velocity is constant, the only variable left that can shrink is the box's mass. This beautifully proves that mass is quite literally converted into light energy. They're just 2 sides of the exact same coin.
Moving right along to Section 2, Schrödinger's equation and mass.
Okay, so we know mass equals energy. But how does mass actually behave when matter acts like a wave? Erwin Schrödinger's foundational equations from 1926 completely shattered the old models. He revealed that subatomic particles do not behave like tiny little billiard balls bouncing around. Instead, they behave as complex probability waves. The wave's amplitude mathematically dictates the actual real-world chance of finding a quantum particle in a specific location at a specific time.
The really fascinating part here is looking at how the abstract mass variable, represented as just m in this highly complex quantum equation, is actually bridged straight over from classical mechanics. If you take the classical formula for a one-dimensional particle's kinetic energy, which is just momentum squared divided by 2 times mass, and you apply quantum differential operators to it, which is essentially mapping how it mathematically shifts over space and time, you get Schrödinger's equation. So at this stage in history, mass was a mathematical necessity fundamentally tied to kinetic energy, but its true physical mechanism in the quantum world was still pretty abstract.
Let's jump ahead to Section 3, Feynman's path integral phase.
To truly grasp how this probability moves and how mass mathematically anchors it, we have to look at 1948 and Richard Feynman's totally brilliant path integral formulation. Feynman proposed something absolutely radical. He said a quantum particle doesn't just take one single path from point A to point B. No, it takes every possible path simultaneously. By mathematically summing over all of these chaotic paths, you calculate the ultimate probability of where that particle will end up. And each path has a mathematical phase based on its physical action. When you superpose or stack all these phases on top of each other, paths with wildly different phases cancel each other out. Meanwhile, the paths with similar phases reinforce each other, creating a concentrated probability wave packet.
Crucially, mass is what dictates this entire phase cancellation process. In Feynman's math, the phase varies in proportion to the square distance traveled. And mass? Mass acts as the exact multiplier for this phase change. So if you have a larger mass, it forces the phase to rotate incredibly fast. When phases rotate that violently over a short distance, they immediately fall out of alignment and just cancel each other right out. What this means in plain English is that a heavy particle's probability wave literally cannot spread out very far. It mathematically anchors the particle in place. This perfectly explains why objects with large mass physically resist movement.
That brings us to Section 4, R-space angular momentum projection.
We've seen all the math, but what is physically happening out there? To answer that, we transition from abstract calculations to actual visual geometry by introducing the unifying mechanism of R-space theory. R-space provides this magnificent geometric visualization of the quantum concepts we've been talking about. Let's break down the R-space projection into a few steps. First, imagine a photon's angular momentum, its pure rotational energy, acting as a rotating phase vector. This phase angle then projects instantly across space, which we perceive as velocity. As these small vortices of angular momentum overlap and superpose, they progress through time. And this geometric projection maps absolutely perfectly onto the chaotic path integrals Feynman calculated.
Let's look a bit deeper in Section 5, vortices equivalent to action. So action, in physics, is basically a measure of the dynamics of a system. Think of it as a physical score of how much effort a process actually takes. By applying the Hamiltonian format of classical mechanics, which maps the total energy of a system, R-space theory reveals something deeply profound. It proves that projecting a quantum phase into space visually is mathematically 100% equivalent to the spatial differentiation of action. The abstract concept of quantum action isn't just a number. It is physically realized as the spinning vortices of angular momentum projecting their phase right into our observable reality.
Which brings us to our final stop, Section 6, Conclusion. What is mass?
Let's piece together all these historic stepping stones, from Einstein's energy to Schrödinger's waves, to Feynman's paths, all the way to R-space geometry, to finally answer our big question. The final piece of the puzzle is looking at the geometry of a particle with mass, like an electron. Unlike a photon, which just has a single rotation, an electron features a double rotation. Physicists call this half-spin. Because it's rotating twice, its phase projection isn't just the tangent of theta, it is the tangent of theta multiplied by the tangent of theta, which equals the distance squared. This geometric double rotation perfectly explains why Feynman's mathematical phase always appears proportional to the distance squared. It's not magic, it is all geometric spin.
So ultimately, mass is not a static property at all. Mass isn't a solid thing sitting out there in the universe. It is simply a dynamic ratio. Specifically, it's a ratio of a quantum particle's internal angular momentum compared to the absolute minimum unit of angular momentum, which is Planck's constant. Mass is, quite literally, pure geometric rotational energy.
And this geometric framework elegantly explains something else too, quantum jitter. The Standard Model tells us mass comes from particles dragging through the Higgs field, but Dirac's equations famously predicted something called Zitterbewegung, which is a microscopic light-speed spatial jitter in particles. R-space theory actually bypasses the Higgs field entirely here. It proves that when multiple angular momentum vortices interact inside a particle, they naturally cause this furious spatial jitter. The greater the angular momentum, the more intense the jitter becomes, and that violent jitter creates real resistance to moving in a straight line. That resistance is exactly what we measure as mass. Which leaves us with a pretty massive realization. Every solid object you know, the chair you are sitting on, the very device you are watching this on, is fundamentally made of waves, phases, and interacting vortices of angular momentum, all jittering at the speed of light. If mass is just a ratio of spinning energy, is the solid world around us simply an illusion? We'll leave you pondering that final thought about the true, dynamic nature of our physical universe. We highly encourage you to explore this source material further. Thanks so much for joining us on this explainer as we unraveled the very fabric of reality.